Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And good day, everyone. What I'm going to do today is to present you my research paper with the title of Optimization of the Location and Array of Sensor using Finite Element Method for Structural Health Monitoring. It's SHM of the nacelle cover on Floating Offshore Wind Turbine, FOWT. This paper has been written by me, Wibowo Hanugroho, with other colleagues, Usnindar Priyohutomo, Nanang Joko Hadipurnomo, and Hendra Adinata. All of us is from Research Center for Hydrodynamics Technology, Research Organization, Energy and Manufacture, from BRIN. The outline of the presentation consists of introduction, related theory, methodology, results and discussion, conclusion, and references. As we know, floating offshore wind turbines are becoming an economically attractive option for wind energy project with the water depth greater than 60 meters. These FOWT are not rigidly fixed to the seabed, and thus their location is not limited to shallow water anymore, and they can cope with strong currents and severe waves. In general construction, the FOWT consists of wind blade, you see in the picture next, nacelle cover, tower, floating foundation, and mooring system. In the study, we focus on the nacelle cover, where the nacelle cover is the protective compartment that contain major component of ocean wind turbines such as rotor and generator. This compartment has to withstand the wind load, dynamic loads, and the weight of the major component inside. In such loads, there's a possibility the nacelle structure can be damaged or has cracks during operation of the FOWT. To handle this problem, we propose structural health monitoring, maybe a solution. The related theory for this paper study is first is the finite element, and then we calculate the using the Hooke's formula, and the stress is strain times the modulus Young, but in the form, the stress and strain in the form of a matrix. Then we finish the equation with the loads on the structure is using a finite element. Then load itself is only coming from wind. It is the formula, half rho CD, the projected area with this wind speed itself. And we're using a drag coefficient is 0.5 from 3D cube body, is coming from the starboard side. This is the methodology. And here we present you the flow chart of the finite element. This finite element we're using automatic generation mesh. This when we do some of the convergence tests by running itself until the stress not change anymore. And after that, we do some sensitivity analysis with this formula. We assume that the sensor reading is from the node of the grid in the point measurement, and the stress itself is the average of the reading. And after that, we do the sensitivity analysis using this formula, where the stress when it's in no damage to damage, then we divided by no damage time, because 100% is the absolute form of that one. So then we can calculate the changes of the stress, and the word is the sensitivity. The methodology itself is we have the selected dimension of the nacelle box is 20 meters times 7.5 meters and times 7.5 meters. This nacelle box is made from carbon fiberglass reinforced plastic, CFRP, and discretized automatically into 43,1943 angular elements and 84,619 nodes. The modeling of the CFRP structure in this study is simplified from an orthotopic material to isotropic one. The loads from the wind speed vary from 5, 10, 15, and 25 meters per second. Wind direction is load from the starboard, as you said before. And the position of the critical crack is selected on the region on the top of nacelle cover near the rotor, and another crack on the region of the bottom of the nacelle cover, close to the gearbox foundation. The top and bottom cracks are assumed to be single horizontal line crack. In the study, FOWT can be assumed to have a good mooring system when the motion of the structure is stable. This makes the wind load have a significant effect on the nacelle as a static load, while response motion due to wave has a minimum effect. Wind direction is also from starboard. Here's some result and the result. This I show you the finite element deformation of the strain. These are almost similar, but there is different because the value of the deformation is different. Here is some result. This is for the single track on the top one. You see here, you can see the pattern on the left side is almost the same pattern for the all speed of the wind. This is what we have in this research. But in here, then we just analyze how the grid distance behave because of the stress itself, because of the crack. You see here, since the pattern of the sensitivity analysis is the same for every wind load, the grid distance analysis can be made by selecting a speed load for the case study. The figures show sensitivity analysis for condition of single cracks located with grid distance 100 meter, 200, 400, 500 on the top nacelle cover at wind load of 25 meters per second. In the figure, for grid distance 100 millimeter, then sensitivity shows the highest value of the percentage of damage condition to no damage is clearly shown that there are 6 dot sensitivity percent above 100. The second highest value goes to 100 millimeter grid distance. In figure B, in this grid distance are 3 dot of sensitivity percentage above 100. While in grid distance of 400 millimeter, figure C, and 500 millimeter in figure D, the sensitivity percent show 2 and 1 dot above 100 respectively. However, all changes in the field stress on the nacelle cover can be detected by all sensors position. But grid distance of 400 to 500 can be selected for mounting the strain sensors on the nacelle cover, which create ease as structural monitoring component equipment. Same as in the multiple crack in the top and the bottom, we detect. So we put a 24-point measurement. It also have a similar pattern before. For all the wind load, it also give a same pattern, but for the grid distance is little bit different. Here the discussion is the grid distance is point measurement all damage condition is also present. However, unlike 12-point measurement on single crack condition, there are 24 measurement required to multiple crack condition. Again, since the pattern of sensitivity analysis in a multiple crack is also the same for very wind load, grid distance analysis can be made selecting speed load for the case study. The figures show sensitivity analysis for condition of multiple cracks located with grid distance 100 to 500 on the top and bottom nacelle cover at wind load of 25 millimeters. For the grid distance 100 millimeter, sensitivity show the highest value percentage of damage to no damage. It clearly show that there are 6 dot sensitivity percent above 100. Stress value above 100% means the sensor position as high difference value between no damage condition and damage condition, and for the necessary to expand grid above 100 millimeter. When the grid distance of 200 millimeter, and 400 millimeter, the sensitivity percentage show 5 and 1 dot above 100 respectively. The lowest value goes to 500 millimeter distance figure with no dot above 100% of sensitivity. However, all changes on the field stress or nacelle cover can be still detected by all sensor position, but 400 millimeter grid distance is preferred to use for mounting strength sensors on the nacelle cover with greater ease as a structural monitoring component equipment. The conclusion from this study we have presented here, it has been found that either single or multiple crack condition on the nacelle cover, the pattern and the sensitivity does not change in any wind speed load. In case of single crack condition, grid distance of 500 millimeter, it is recommended for mounting the strength sensor on the nacelle cover as structural monitoring component equipment. In case of multiple crack condition, grid distance of 400 millimeter is recommended for mounting the strength sensor on the nacelle cover as a structural monitoring equipment. In general, application of finite element method to determine optimum location of the stray of the sensors offer great potential for detecting and locating damage in a structured nacelle on FOWT at the early stage. Minimum number of sensors for detection is 12 sensors in the critical position, like in the cover base of nacelle. For the best result of predicted structural monitoring, more the number of sensors recommended. In ideal condition, if array of strength sensor want to be applied in the nacelle construction, the whole of the structure can be covered by this array sensor with a grid distance of 400 millimeter. This is some references. You can see also on my paper. The acknowledgement, we need to be very highly appreciate of the research grant from Disaster Technology Program from the Research Organization for Energy and Manufacture, National Research and Innovation Agency Indonesia to conduct this study. Yeah, thank you very much for your attention. If you have any question, any comment, please don't hesitate to ask, and maybe I can answer, or if not, then we can do discussion later. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.